So this is number 77 from page 591. And the question here is asking that you have electric field intensity between two charged plates. So you know that the electric field intensity is 1.5 times 10 to 3 newtons coulomb. You have two plates that are separated. Basically, you have a plate here, separated by 0.060 meters, or basically 6 centimeters apart. So you know that that's your R or your D, which is 0.06 meters. You're asked to find the electrical potential. So you need to look in your notes to look for the short equation that I gave you last class, which is V is equal to E times D. And basically you just plug in the numbers, 1.5 times 10 to 3 times 0.06, and this gives you the electrical potential. Remember, electrical potential is measured in volts. So the final answer you should get is 9.0 times 10 to the power of 1 volts. So that's your electrical potential between these two plates. And that's 77. Moving on to the next question. What's the next question here? Number 80, I believe? That's right. Number 80. So this one is your Millikan's experiment example. You have your diagram where, again, you have your two plates. So positive in the top, negative in the bottom. And you have a drop that's suspended. So remember, when it's suspended, it's not moving. That means that it's levitating in between these two plates. So because it's levitating, you know that the force of gravity is equal to the force of this electric field that is applied to that drop. So what's given here? The oil drop shown in the figure is negatively charged and weighs about, weighs exactly 4.5 times 10 to negative 50 newtons. So this is already given to you in newtons. So it's not really the mass. It's already multiplied by the gravity. So this should automatically tell you that it's Fg. The oil is suspended in the electric field and it has a strength of 5.6 times 10 to the 3 newton coulombs. So what is the charge on the drop? Okay, so you have to use this information that it's suspended. So the force of the electric field or force of gravity is equal to the force of electric field, or they're just equal. We know that force of gravity is that because it's in newtons. That's the force that's applied on the drop. So it's 4.5 times 10 to the negative 15 newtons. Now, what can we do with this force of electric field force? We can change this into the equation. Remember, this is exactly the same as Q multiplied by E. If you arrange the formula, if you rearrange this formula, you will get Q times E for force. Do we have E? Yes, we do. Do we have Q? No, we don't. That's what we're trying to find. So I'm going to isolate Q by itself by dividing by E to both sides. 4.5 times 10 to negative 15 newtons, divide by E, which is 5.6 times 10 to 3 newton coulombs. So the charge here for the final answer for number 80, let me double check my paper, is 8.0 times 10 to negative 19 coulombs. So that's the charge of your point charge. The second part, you always will be asked the number. How many electrons are in that drop? Since we apply this amount of electric field to hold this up, so there's a relationship about how heavy that drop is to how much force, electric force, is applied to keep it up. So we know that for every 1 electron, we know from Millikan's example is that you have a charge of 1.6 times 10 to negative 19. That's your charge for 1 electron. So since you have this 8.0, that's just a printer printing, times division bar, electrons on the top because this is what you want, So for every 1 coulomb, you have 1.6 times 10 to the negative 19. I totally messed this up because the printer is throwing me off. Okay, let me redo this again. 8.0 times 10 to the negative 19 times division bar. Okay, so coulombs is at the top. We're still aligned here on camera. Coulombs at the top. So because that's the one that we need to get rid of, put coulombs in the bottom. The electrons is what we want. For every 1 electron, we have this charge. So if you did 8.0 times 10 to the negative 19 times 1, divide by that, your final answer is going to be 5 electrons. So in that little charge that we did, that is kept up by this electric force, there are 5 electrons in there. That's pretty cool. And that is Millikan's example. That's what he did, and that's how you calculate it. Just the key thing here is that you need to know that if it's suspended, electric force is equal to force of gravity. Pay attention to units. In this question, the force is already given to you for force of gravity. Sometimes you're given the mass, which you need to multiply by gravity. But in essence, it's exactly the same step. So that's it. So for next question, for number 99, I realized that I gave a question that you cannot solve. So ignore 99. There you go. So continue on your magnet stuff. Thank you.